This talk has three parts. The first is, why emulators? Product-like prototypes of exoskeletons and prostheses, like this device I designed as a graduate student, take many years to develop, are specialized and inflexible, which limits their utility as experimental tools, and frequently do not deliver the intended benefits to humans. Instead, we use versatile device emulators. They have powerful off-board motor control hardware, lightweight instrumented end effectors worn on the leg, and flexible tethers connecting the two. They allow experimental tests of new assistance strategies on humans in days rather than years. This paper presents a new prosthesis emulator system. The end effector has two independently actuated toes. Moving them together produces plantarflexion, and moving them in opposite directions produces inversion-eversion. This is the first prosthesis with control of both plantarflexion and inversion torque. The two-toe approach results in a simple structure weighing only about 700 grams. It also couples the feasible region of inversion-eversion torque to plantarflexion, but typical values lie within the feasible region. The end effector itself has no spring, and so series elasticity comes only from the tether. Higher transmission stiffness is expected to increase closed-loop torque bandwidth when the toes are fixed, but at a cost of increased sensitivity to unexpected position disturbances of the toes. In this case, benchtop tests reveal a good balance between the two, with critical frequencies of about 20 Hz each. These measures denote exceptional responsiveness and disturbance rejection for a robotic prosthesis. Walking trials demonstrate that a wide range of inversion torques can be tracked, from 0 Nm to plus or minus 30 Nm of inversion, with only 1 to 2 Nm RMS error, that's 1 to 4% of peak. These values again denote exceptional performance. Torque is tracked using a combination of proportional control, damping injection, and iterative learning that Zhuan Zhang will describe on Friday in the Exoskeletons 2 session. So what will we do with this unique new system? The primary application is to study balance in amputee walking and develop new balance-enhancing controllers. For example, we recently showed that once per step modulation of ankle push-off work can reduce balance-related effort during walking. We expect greater improvements when mediolateral center of pressure can be controlled as well. We also expect this platform to contribute to improved prescriptions, which Josh Caputo will explain on Friday in the Prosthetics and Neurorobotics session. Finally, we expect that the results of experiments with this system will help build a foundation for the rational design of autonomous devices, like these unpowered ankle exoskeletons that reduce the metabolic energy cost of human walking. Thanks to the National Science Foundation and the National Institutes of Health for supporting our work.